short extra credit problem for you here. So I'll call this a note in addition to class, something you should know if you go into certain science classes and so forth, that you don't really need it to solve math problems per se, but it pertains to real life. Given a sine wave, which we're referring to these, y equals a sine dt minus c plus d, or y equals a cosine dt minus c plus d. We call both of these sine waves, the cosine is just the sine shifted over, same shape. One of those kinds of things. What did we do before? Well, first of all, we said the amplitude was A. Absolute value, right? It's always a non-negative number. The period, P, was 2 pi over V. So we can calculate those things. But there are a couple more things that people sometimes ask you about these things. In physics, for instance, if you ever take first year physics, they might ask you, what's the angular velocity? I'm sorry, the angular frequency. What is that? This is actually very easy. It's B. Whatever multiplies T there is B. Now I put T here instead of X like we usually did in our graphs, because what happens in a lot of practice, like electronics engineers, this might be the current as a function of time, or the charge as a function of time or something. And so T is more natural for time. And also in physics and engineering, a lot of times instead of putting B here, they'll put omega. They like a little omega for the letter. So if you see that, then omega is the angular frequency. But it's whatever multiplies T. For us, that'll be B using the notation. Somebody asks you, that's what it is. And then we have frequency, which is what you'll see if you go in your electric box in the back, right? It'll say frequency is so many hertz. Or you'll see it on these chargers that you plug in for your electric devices around the house. Frequency is just B over 2 pi. Right? So there's angular frequency B, and this is in radians per second, if T is in seconds. But this one is in cycles per second. Cycles per second. Cycles per second is, you can use SEC or S. The international standard is used S per second, but SEC, the old abbreviation, holds on somewhat. Cycles per second is too long to write, so a lot of times 4 cycles per second, they'll write Hz, which stands for hertz, Hertz. And this means cycles per second. And furthermore, this radians per second, sometimes you'll see it written as, since radians are unitless, 1 over seconds. That'll be the units, it's 1 over seconds. So I'll just mention that for your science classes. And now, extra credit problem for 5 points. If you send it to me today, after today is no good, all right? By midnight. Write this down and send it in. You don't have to do anything but copy what I say. I think since you're learning something, it's worth a few points, right? And some people ask about grading. Here's what I'm going to do on the grading. I'm going to drop your lowest 100 points. It can be the final exam. If you've got A's on all your tests, you can check with me if you're not sure. Then you don't have to take your final exam. I'll drop that one and you got an A in the class, right? But I'll drop your lowest exam, and then on the remaining 4 exams, 3 midterms and a final, or all 4 midterms, I'll add those scores together, plus your extra credits, the one at the beginning of the course for 10 points, and this one for 5 if you do it. It's easy, 5 points, you just copy this down. And if that's higher than the sum of the cutoffs, right? For 4 tests, 360 points gets you an A. If you add up to at least 360 points with your 4 tests and your up to 15 points for extra credit, then you've got an A in the class. If you add your 4 tests together, and you've got at least 320, 80% of the 4 tests, right? Then you've got a B in the class. If you've got, so 320 to 359, and then you've got at least 280, you've got a C, and if you got 240, you got a D, right? So that's how I'm going to grade. I'm going to add up your scores. I'm going to add up the cutoffs, 90, 80, 70, 60 for 4 tests, and whichever is higher, I will, if your tests are higher, you'll get the grade, and if not, you won't get the grade. Also, it's possible if the final's too hard, that I might curve it a little bit, and then you won't have to get like 360 for an A. Like if I curve it 5 points, then you'll need 355 for an A. All right. Here's the extra credit problem then. Find the angular frequency. Oops, I gotta move this camera over, huh? Oh, it's okay. Angular frequency, amplitude, and period of the sine wave y equals -2 cosine 3x minus pi over 6. Wonder what that is. Well, we already did some of these. Amplitude. Just absolute value of A, absolute value of -2 is 2. So just copy this down and send it to me. Right? And then the period, P, is 2 pi over B is 3 here, right? So it's 2/3 pi. And I should have mentioned something here. Frequency is actually B divided by 2 pi. Makes it actually 1 over the period. They are reciprocals of each other. The frequency F is B over 2 pi, or it's 1 over the period. If you calculate the period, the frequency is just this reciprocal. Then the angular frequency is 2 pi times the frequency, right? So if you want, once you know one, you know the other, right? So here's the amplitude, here's the period things we did before. Now I want to add to that. What's the angular frequency? Somebody asks you that for your physics class or something. Oh, it's just this number 3. I have to just read it. And what's the frequency? You just divide that by 2 pi, or you take 1 over the period. Frequency F is 3 over 2 pi. Turn the period upside down. Easy as that, right? So now you learn something. Send this part right here to me for 5 points. Make sure you send it from your own email address so I never forget it. Now on to the questions here. Please ask questions as we go along. I already had one request for 28B. Let me just look at 28 and do that for some examples. I'll do the whole problem. But feel free to interject comments as we go along. I've got the sound all the way up, it looks like. Yeah. So what if I ask you to convert this to polar coordinates, or convert each equation in polar coordinates to rectangular coordinates? So convert to rectangular coordinate. R equals -3. What is that? Well, we don't have an R given explicitly in polar coordinates, so we write equivalently R squared equals 9 by squaring both sides, but then R less than or equal to 0 because I've introduced a new solution, R equals 3. But then I realized that this is x squared plus y squared. We do have an expression for R squared. R squared is x squared plus y squared. Tangent theta is y over x squared. Conversion equation. So this is x squared plus y squared equals 9. That's what it is in rectangular coordinates. And I can drop this R less than or equal to 3 because when I let R be -3, what I'm doing is I'm taking all arbitrary angles, and at each angle I go -3 units. I go 3 units the opposite direction. So when I'm pointing here, I go to here. Then as I turn the angle around, I just keep going to the opposite side 3 units out, and I trace out the whole circle. R equals -3 is all points backwards 3 from the origin. It's the same circle as R equals +3, right? So I don't need to put the restriction. It's still the same set of points, right? So if I ask you to sketch it, it's the circle. On the exam, I may ask you to sketch it. Well, it better not since it wasn't on the problem. I'll word these like the problems. And I'll just give different equations, right? So R equals a fixed number is just a circle whose radius is the absolute value of that number. Remember that when you get out of this class. That's an important concept of polar coordinates. Circles are easy. Circles at the origin are easy, right? Theta equals pi over 3 in part B. How do I convert that? I don't have theta in my conversion, but I do have tangent theta, so I'll take tangent of both sides. Tangent theta equals tangent pi over 3. What is tangent pi over 3? I run to the unit circle, and pi over 3 is 60 degrees. I recall the memorized circle. I told you need all semesters, so we did. Square root 3 over 2.5. Tangent is this side over this side. And the 2's are both denominators, so they cancel. And the equivalent equation is tangent theta equals square root 3. How about that? I have to be a little careful on this, but to think if these are really equivalent at each step. I can't take tangent of pi over 2 or 3 pi over 2 because it's y over x, and when x is 0, it doesn't work. But the only place where x is 0 on this one is at the origin, and that's still a solution to this equation. So you just think about it and realize you haven't lost any points. If I'd asked you for the graph of this, tangent, I didn't finish today. Tangent theta is y over x. So y over x equals square root 3. Multiply both sides by square root 3, and what you have is the line y equals square root 3x. And y equals mx plus b form, you realize the slope is m equals 3, and the y-intercept is b equals 0. So it's a line through the origin of slope square root 3, about 1.7, something like that. So there's what the graph looks like. I didn't ask you for that, but be able to compute this, right? There's 28b. So theta equals a number is a line through the origin. R equals a number is a circle of radius absolute value of that number, not the origin. And then finally, on the last one, this is the thing you're more likely to get in future classes. Well, I'd say more likely to have be hard. These probably actually come up more, come to think of it. The third one is 2 sine theta plus cosine theta equals 0. These should look familiar, right? How do I convert that? Again, I don't have a sine theta or a cosine theta in my conversion equations for polar coordinates. Here's the conversion equations you need, right? R squared equals x squared plus y squared. Tangent theta equals y over x. That's how we convert from x, y to r theta. And so that's what I use here. I got tangent theta instead of theta. I got r squared instead of r. The other two that you can use are x equals r cosine theta and y equals r sine theta. So if I have r sine theta or r cosine theta, I don't have this here, but if I multiply both sides by r, I have 2r sine theta plus 2r cosine theta equals 0. And that's an equivalent equation, right? I have to be careful because I multiply here, I made r equals 0 a solution. That's the pole, the origin. Was the origin a solution here? Yeah, it was. If I put an angle 3 pi over 4, not 3 pi over 4, if I put in the right angle, just right, I can make 2 sine theta equal minus cosine theta and make this be 0. And so at just the right angle, I can make r equals 0 solution to this one. So I didn't introduce any new points, even by multiplying through by r. This is an equivalent equation, but this one is 2y, right? Y is r sine theta plus, oops, this was not, plus r cosine theta. X equals 0. This is the line y equals minus a half x. About that, a line through the origin with slope minus a half. So there's one of them. Now I want to point out a few things. One thing I need you to be able to do when you come out of this class is write triangles. I mentioned this in the first test, but I'm going to ask you again on the final. You have to be able to do right triangles. It's one of the major topics. Let me take the problem off of here. I'm going to have some problem to solve a right triangle in there. Suppose I ask this one. If A equals 8 and B equals 3 centimeters, solve the right triangle. There's a tacit assumption going on here, right? In a right triangle, that A and B are the legs and C is the hypotenuse. So I'll put 3 here and then A and B, it doesn't matter how I put them. I can put 8 here for A and 3 here for B or vice versa, just so that they're the legs. Now opposite A ought to be alpha. So opposite 8, I put alpha, and opposite B goes beta, so make sure you label these correctly. And now I need to find C, alpha, and beta, right? In these right triangles, I'll give you either two sides or an angle and a side. I expect to be able to solve it. Angle won't solve the triangle, isn't it? So how do I solve this? I write a right triangle trig relationship that relates the two pieces of information I know and one I don't. What's one I don't? Well, I noticed that the tangent of this angle is this over this, right? So I'll say tangent beta is 3 over 8. Relates two numbers I have and the one I don't. Then in a right triangle only, I can say beta automatically is the arctangent of 3. Why? Because in a right triangle, these two angles are acute. They're between 0 and 90 degrees. That means that the solution, whatever it is, can only be arctangent. Arctangent of a positive number will be between 0 and 90 degrees. So this will be the unique solution for a right triangle. Just take tangent beta is a number, beta is automatically the arctangent of a right triangle. What is that? I need to run it on a calculator. Make sure it's in the right mode. I want degrees out. I don't know what it said in the instructions. All right, your answer is rounded to the nearest tenth with angles and degrees. So I'm going to put my calculator in degrees mode. It is. And arctangent is evidently 20.556 and a bunch of others. As it rounded to 1 decimal place, right? Yeah, nearest tenth. Look at this decimal place here. That's the last one I'm keeping. The next digit is 5 or greater, so I round this to 20.6. And then I use the same units as the original triangle, put the units on. 20.6 centimeters. Okay. Now, I have two more things to find. Once you have one angle in a right triangle, the other one is complementary. It's always 90 minus that one, right? Oops, that was not centimeters. I apologize. That was degrees. That was an angle. Sorry about that. 90 minus 20.6 degrees gives me 69.4 degrees. So that's the last angle. And now I get the last side. Whenever you have two sides of a right triangle, the easiest thing is to use the Pythagorean theorem. So I'll just say the last side C, use C for the hypotenuse in a right triangle, and in oblique triangles it doesn't matter. C is the square root of 8 squared plus 3 squared, right? So it's a squared plus b squared equals c squared. Let's see this. 64 and 9 is 73. C is the square root of 73 exactly. If I ask for exact numbers, you leave it as square root of 73. However, here I've asked for nearest tenth, so you have to run it on the calculator and you say square root 73, close the parenthesis, and I got 8.5 4, etc. So that round, since the next digit is, oops, 8.54. Since the next digit is 4 or less, I round it down to 8. So there's that one solved. Questions on that one? You get one on that. I want you to be able to do these arc length and area of a sector problems. That's one of the topics for the course, and also the angular speed stuff. So let's look at, and we can do some of these others too. 4A, what is the area of the circular sector? From a circle with r equals 3 inches and a central angle of 20 degrees. This is one of the easiest formulas. It's not that easy, that's a little bit easier. But area is just 1/2 r squared theta was what we proved from taking the fraction of the area of a circle. Right, if you put in 2 pi for theta, then it gives you pi r squared, the area of the whole circle. So how do we calculate this one? You simply put 1/2, oops, times 3 squared times 20 degrees, and you're wrong. Why? This formula only works in radians, so you have to convert this to radians. 20 degrees times pi over 180. Now, I think I've asked you for an exact answer on this problem. When I ask you for an exact answer, make sure you simplify the result. So what can we do? We say 20 over 180. We can cancel the zeros, right? We're dividing top and bottom by 10. And I've got 2 over 18. Well, that's 1/9. So this is actually just pi over 9 in here. Right? And then here I have 1/2 times 9 squared. And now I notice the 9's cancel. This whole thing reduces to pi over 2. I want to see that, not this mess up here, right? And then what are the units? It's an area, so it's square units. If this was in inches, then I have pi over 2 square inches. Make sure you convert these angles to radians before you use that formula. And for B, similarly, 4B, what's the arc length subtended with the same angle in the same circle? All right, so we've got this picture. You can draw it here. A circle of radius 3 inches, and I went 20 degrees, something like that. A little less than 1/4 of a right angle. And this was the area. The arc length is just this distance here along the edge, right? That's what you usually call it. This is the easiest formula semester. S equals r theta. How about that? So r is 3 inches and theta is 20 degrees, but the formula only works in radians. So you multiply it by pi over 180 degrees. The degrees cancel, and now this is radians, which is unitless and it drops out, and 3 is what, inches, and so the whole thing is in inches. Again, 20 over 180, the 10's cancel, you got 2 over 18 is a 9, so 3 times pi over 9. But that's just pi over 3 inches. Right? Since it's a measure along the edge, it's a length. Okay, let's look at number 6. This one's a little trickier. This is dealing with angular speeds. You do the physical sciences. This comes up. What is the exact angular speed in radians per second of an object rotating at linear speed 12 feet per second? That's the speed of a point along the circle. Along a circle of radius 5 feet. How about that one? Now remember this formula, V equals R omega. This one should be easy to remember because what you're doing is you're just taking your old formula, F equals R theta, the easy one for arc length equals radius times angle subtended, and divide both sides by T. Angle divided by time is angular velocity omega. Distance divided by time is linear velocity V. So you just divide this one by T and you get this one. I'll leave that off, but just say that if you forget it, you can figure it out. Right? Write this down because what you have here, 12 feet per second linear speed is V. And here's R equals 5. When I put those in, I have 12 equals 5 omega. I divide by 5. I've got omega is 12/5. What is that? Well, this one is in feet per second. This one is in feet, so it's just per second. All right? Feet per second. Divided by feet. So the feet cancel. And you get omega is 12/5 per second. That's what I want. Radians is unitless, so you can also write radians per second. All you had to do was divide. Huh. How about this one? Cotangent of 150 degrees. I will almost certainly ask you something like this. This is 5A. With the cotangent of 150 degrees, your calculator won't have that, right? And some of these online calculators, you're going to check your answers by check your answers on the online calculator. But I'm asking you to do the steps, and some of these I'll try and make them so you can't just do them entirely online. How do I do that exactly? And by the way, when I put these, I'm going to say exact, so don't just put in, get a decimal approximation. I can remember that cotangent is cosine over sine, right? Cosine 150 over sine 150. And now I've calculated exactly on the unit circle. 150 degrees, let's see, it's 180 a straight angle except for 30. So it's 180 back up 30. There's 150. Well, if I back up 30, then 30 is the reference angle. And I know from memorization, this is square root 3 over 2. This is 1/2 on a circle of hypotenuse 1, the unit circle radius. Consequently, the coordinates of this point are minus square root 3 over 2 and plus 1/2. That's the cosine and the sine of this angle, right? Cosine first. Have to have the unit circle down for this test. So cosine over sine is just this one over this one. This is equal to minus square root 3 over 2 over 1/2. The 2 is both denominators, so those cancel, and I just get minus square root 3 over 1 or minus square root 3. There exactly is the cotangent of 150 degrees. You can check your answer pretty easily too, right? All you have to do to check your answer, calculator or whatever, is take 1 over tangent of 150 degrees. And that will check it, see if you get the same decimal that one as if you have a decimal calculator. Anything else in particular you'd like to see yet? I'll tell you what else I'm gonna do. I'm gonna do an oblique triangle. I'm gonna give you a right triangle. I'm gonna give you an oblique triangle. Let's just solve triangles when you get out of this class, right? Maybe you'll have to save somebody on a desert island sometime. Do a triangulation scheme for them. Although it's, when they do that on faraway islands, the Earth is not flat like a plane, so they do spherical trigonometry instead of plane trigonometry, which is what we do here. It's very similar. You can pick that up once you get out of this class if you were taking interest. All right. Triangles on the Earth work reasonably well if the island's not too far away. How about this one? This is 10B. On your last test, I really, in regular class, I usually go over the exams in class, so everybody learns a little more from that. We had a problem on that side-side angle thing. There were two answers, and people who put it into a machine to have the machine solve a triangle only got one of the triangles and lost a lot of points. Make sure, for the final, that if there's two triangles, you solve both of them. So here's what we have on this one. It's a two-answer problem. It's A equals 20, alpha equals 40 degrees, B equals 25. Solve this oblique triangle. If I don't say it's right, then assume it's not right. You just have to be lucky to get a right triangle after that. For an oblique triangle, I always give you three pieces of information other than angle, angle, angle. And you have to figure out three. So what do? I highly recommend on these that you draw the picture. So I'll draw B 25 units long. Then I'll draw A a little shorter, 20 units long, but I don't know what direction it goes. Maybe it goes like that, about 4/5 the length. And then alpha is 40 degrees, so this is A. Has to go opposite A, so it must go over here. It's almost half of a right angle. There it is, and it goes off here, but I don't know how far. So this is 40 degrees, that's alpha. This is A over here. That looks about right the way I drew it, right? So here's a triangle. Maybe it's this triangle. 40 degrees, A is 20 now. Triangle might look about like that. Now I realize to my horror, that's not the only triangle, right? This is the dreaded side-side angle case, the ambiguous problem. It might have zero solutions, it might have one solution, it might have two. You can use the law of cosines to solve this if you want. It does actually work that way kind of nicely, but we didn't do that in class. Most textbooks don't. The textbooks tell you, and this is what we did, is if you have side, 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 or side, angle, side, you do the law of cosines. And otherwise, you do the law of sines. So side, side, angle, a bad case, is a law of sines case. Even though for this one, law of cosines works, we'll do it that way. So side, side, angle, law of sines, I need to relate the three numbers that I know and one that I don't. For that, I need to use this side and opposite angle. So I will say sine of 40 degrees is to 20 as, and now I need to put this other number in here. That's 25 as B, so this must be beta. What's left, 20 and 25 are A and B, so this one must be C. On oblique triangles, it doesn't matter which side you call A, B, C. Just put A opposite alpha, B opposite beta, and C opposite gamma. So opposite C, I have to put gamma. And I'm trying to find beta, gamma, and C of this triangle. Let's see. Sine 40 is to 20, its opposite side, as sine beta is to 25, relates the other numbers. There it is. And now I say side, side angle, I might have two solutions. Can I see another one? What you think is this angle has to be the same, but it could be arbitrarily long. This side length can swing, this side can swing around any direction. So I have a circle of points where this thing can go. And if it goes right here, you get a colored chalk. Here's another way you can reach this side with and be 20 units long. So this is the second triangle. It looks like this. 25, 20, and C up here. And then this is beta. And this is gamma. So it looks like there's two possibilities. Sometimes it's hard to tell from the drawing. This one looks pretty clear. But what always happens is if you just continue the problem, you can prove it. You can prove whether they're 0, 1, or 2. Here's what you do. You're trying to find 3 more pieces of information in each triangle. This one I allow to solve for beta. I multiply both sides by 25 using algebra. Put them in the equation. And I get the sine beta is 25 sine 40 over 20. Now, if sine beta is equal to this number, what's beta? Unlike the right triangle where it's always arc sine, for these oblique triangles, sometimes there's 2 solutions, right? Case 1, arc sine is still a possibility. Beta equals the arc sine of 25 sine 40 degrees. I need to move it. Arc sine of 25 sine 40 over 20. But there's another possibility. First, let's see what this one is. If you try and compute this one, and it says domain error, guess what? Either you made a mistake or this has no solution. When you've done this correctly and you get domain error, there's 0 solutions. Remember, the side-side angle can have 0 solutions, 1 solution, or 2 solutions. But if this angle was steep enough, this 20 sine of length 20 wouldn't be able to intersect it, right? So the angle is not so steep I can't intersect, but there actually will be a solution. But if this gets to be a number bigger than 1, there is no arc sine of a number bigger than 1 because there's no angle whose sine is a number bigger than 1. Let's try this one. This one does work out. Inverse sine 25 times sine 40. Make sure you close your parentheses after this. If you don't close this in parentheses, but leave it open on some of these old calculators, it'll take the sine of 40 degrees over 20, right? And close the parentheses automatically. It'll take the sine of 2 degrees. You don't want that, right? So close your parentheses here. 25 sine 40 close divided by 20. And now I get 53.46 degrees. Suppose I'm rounding to 2 decimal places. So I've got that. So there's at least one triangle whenever I don't get a domain error here. So maybe there's another one in the side-side angle case. What's the other angle? We showed in class that it's always 180 minus this one. So we try beta equals 180 minus this one. And we don't have to recompute arc sine of 25. Hold on here. I don't need to recompute arc sine of 25 sine 40 over 20. I've already got it. Here's what you can do. On your calculator, just put 180 minus second answer. Enter. And it will carry this entire number here that you just did on the last display and subtract it from 180. Or you can do this in your head a lot of times. If I take 180 minus 53.46, let's see, I got 36.54 looks like. If I subtract in my head. Not 36, 136. No, 126. Oh, golly. Sorry. That's why you're doing the calculator sometimes. 126.54 is 180 minus this one. And I can do it this way to get lots of decimal places and then round. All right, once I've got that angle, now I can proceed. Remember, Once I have two of the angles in an oblique triangle, I immediately just find the third one. So here's the first thing of the three I need to find on these. The second one, I'll subtract 180 gamma is 180 minus the two angles that I know. 53.46 I found. 40 I was given. Plus minus 93.46 gives me 86.54 degrees. Yeah. And similarly over here, this one, gamma should be 180 minus the two angles I know. 126.54 and 40 degrees. Well, let's see, these are 166.54. That leaves me 13.46 degrees. Now, if there's only one triangle that solves, what you'll find is this will come out to be negative. If this angle comes out to be negative, then you know there isn't a second solution. You throw this one out. So it's pretty easy. If when you take the arc sine, you get domain error, there's no solutions. If when you go to calculate one of these angles, it comes out negative, there's only one solution. Right? Now, since I got a non-zero angle here, I know there actually is two triangles this time, and I just have to go and find the last side. I can use the law of sines again. So I'm solving these oblique triangles with the law of sines, right? The side, anything but the side, 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 or side angle side cases. I use the law of sines to find two of these. I use the sum of angles theorem to find the last one. Right? Now I'm going to go back and use my original numbers just in case I made a mistake here. I won't compound my mistake by putting a bad number here. Let's say sine 40 degrees is to, that's the sine of alpha is to A20. That's what I was given, so this should be right. Equals sine gamma, 86.54 degrees, over C will give me the last thing I need to know, C. Right? Well, if I would have been smart, maybe I would have written this upside down. Let's turn it upside down now, right? Because the law of sine goes right side up or upside down. 20 over sine 40 degrees equals C over sine 86.54 degrees. And I multiply both sides by 86, sine 86.54, and we get then the C equals 20 sine 86.54 over sine 40. Now run that in the calculator. Close this parenthesis here, it'll take the sign of more than you want. I get 31.06. Now the first case is solved. Right? Second case, I just do the same thing. This time, I say sine 40 is to 20. Same thing I wrote over there. As sine of the angle gamma here. 13.46. Here's the C. And I just have different numbers to solve in the same kind of equation. Let's see what I get. Again, I take reciprocals. I should have done that in the first place if I was clever, right? 20 over sine 40 degrees equals C over sine 13.46. Multiply by sine 13.46, and I get C equals 20 sine 13.46 degrees over sine 40 degrees. Comes out to be and the answers to these are on the back, so you can check them. I get 7.24. That doesn't sound like what I got before. Let's see what I compared on this one. Oh, I ran it as the nearest degree on there, so that is right again. And the answer is I ran it as the nearest degree. That looks okay. Okay. Comments on this one? If there's a side-side angle, make sure you get both triangles or however many there are. No rules for solving right triangles and for solving oblique triangles. Well, I haven't left myself a whole lot of room for asking applied problems. If I give you an applied problem, there's not so many in here. There's a good chance you'll get this one. Go back here. Let's look at number 30. We said before, this is a classic problem. We'll just do another one like it here. Suppose you have two observers looking up at a tall tower here. And you want to know the height of the tower. One observer standing further back measures the angle up as 18 degrees. The forward observer measures 25 degrees. And the distance between these observers, they pace it off as 1,000 feet. Wonder how tall the building is. Write in on these applied problems the numbers you know, all of them, and what you're trying to find. Then you can try and do them. Now, one of the advantages of the triangle is, we'll assume this is a right triangle, unless I say otherwise, right? Is that you can look at it and sometimes see some additional information, because right now I'm stuck, right? This triangle, I only know this one angle in the right triangle besides the right angle. I can't solve it unless I have two sides or a side and an angle, two pieces of information. In this right triangle, again, I only have one angle. I don't have this side or this side or this side. This isn't a whole side, so I don't have enough to solve that. Here's an oblique triangle. There's three triangles in here, but I only have two pieces of information there. This one and this one, I need three, right? So what am I going to do? I'm going to look in the diagram for something that's going to help me to figure some more. And I noticed this angle and this angle are supplementary. So I immediately compute this one and say it's 180 minus this one, 25, is 155 degrees. Now I've got it because I've got angle, side, angle, right? I can solve this oblique triangle given angle, side, angle with the law of sines. Or if I want, I now know that this, since this is 155 here and 18 here, this angle must be right 180 degrees in the triangle, less this angle, less this angle. And I get 7 degrees for this one. So I know a little more than that even. So I can also use angle, angle, side and solve it. I can use whichever one I feel comfortable with. Suppose I use angle, side, angle. Then I'm using the law of sines, right? Anything but side, 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 or side, side, angle is law of sines. And let's see, I need angle on its opposite side. Let's see. You know what? I think it's easier to use angle, angle, side, come to think of it. So I use side, side, angle. I've got to. Let's use angle, angle, side. We'll say sine of 7 degrees is its opposite side. For a lot of sines, I need an angle on opposite side. So this is the only place I have an opposite side. And then let's try and find this one. I can find either this one or this one because they don't have two pieces of information in the right triangle either way. It doesn't matter. Is equal to, if I call this C and try and find it, sine of its opposite angle, 18 degrees over C. I see some people put these together wrong, right? In this law of sine, you have to put the sine of the angle with its opposite side in the triangle. Sine of this angle with its opposite side of the triangle. Both in the same triangle. Right? So do that, and then you'll get this, right? Again, turn this upside down. 1,000 is the sine 7. And C is the sine 18. Multiply both sides by C, by sine 18, and I get 1,000 sine 18 degrees over sine 7 degrees. Must be the measure of C. What's that? Again, being careful on the calculator. I get 2535.6. But I'm not done. Let's put 0.64. Be careful on here. I've seen sometimes people round these to too few digits and wind up with poor results. These angles presumably are exact measures. If these are exact measures, then you want to carry a bunch of digits here, because when we're all done, how tall is this height going to be? If this is 1,000 feet, I'm probably going to need to measure this something at least 1,000. So I'm going to have these 4 digits and then point something. And the question is to round to the nearest tenth. So I need at least 5 significant digits. Remember how significant digits work? If you multiply two numbers like 23.5 times 8.7, how many digits did you carry in your rounded result? We didn't talk about this much in the semester, right? You count significant digits. You start from the leftmost non-zero digit and you count over till you run out of digits that are significant. 1, 2, 3. So this carries 3 significant digits. This one, however, only carries 2. When you multiply these numbers, maybe I should do it. 23.5 times 8.7. You get 204.45. Great. This is garbage. If these are rounded numbers, the most digits you can expect to be significant are 2. So you normally round this and say this is approximately 200 is where you round it to. The digits after that are not significant. So I would say it's approximately 200 in that calculation, counting these two as significant. And that's what you do when you round these things. After those, this digit could be anything depending on what the numbers I truncated here. If this is 8.74, it might be 208 or something. And if this is 8.65, it might be 191 or something. And so this could be quite a lot off in the last. If I try to carry a third digit, it's garbage. It could be anything.
This is a multiplication, right?
Yes, multiplication.
23.5 or 8.7. Where to get those?
I just made them up. I said, suppose I was multiplying these two numbers. The rules of rounding say that when I take the result, which comes out to be this exactly for these exact numbers, if these are rounded numbers, I call it approximately 200. And I say these two digits are significant, but this 0 isn't. And you only, if the least number of digits is 2, and the number's being multiplied, you only carry 2 significant digits, because the next digit could be anything. This could be between 190 and 210. I don't know what it is. So that's rules of rounding. You carry when you do multiplications, divisions, or these trig functions, you carry only that. And if I were to round one of these things off to 2 digits back here, my result would only be good to 2 digits. It's trouble. And I've asked you to round it to the nearest tenth. So assuming these angles are exact, otherwise we can't get this to the nearest tenth, then we want to carry lots of digits here, or we won't get it the right answer to enough digits. So there's C, and now that I have C, I have a right triangle. I can sneak in both oblique and right triangles in this problem. This is a great problem in the final. Now I have this side, and I want to find this side. I have this angle. I write a right triangle relationship that relates these 3 things. All right, so I'll say, oh, that's tangent of this angle. It's this one over this one. Oops, not that. Sine of this angle is this one over this one. So sine of 25 degrees is H over C, which was 25, 35.64. I multiply both sides by 25, 35.64. I get H equals that times sine 25 degrees. Again, we'll pretend that 25 degrees is exact, or at least carries a lot of digits. Multiplying that out, and here's what you can do also. If this number is already in the display, you can just push times sine 25. Close the parenthesis if you have an old calculator, and push enter. And what that will do is we'll take whatever number was on display multiply that times sine 25. You don't even have to push second ands. Whatever numbers the display is automatically multiplied. You'll see it on the screen. Now, I've done a calculation since then, so I can't do that, but let's try this. 25, 35.64 times sine 25. And I get 1,071.61. Let's say this is approximately 1,071.60 and a bunch of other stuff. So it's equal to that. Is approximately 1,071.6 feet, the same units that was over there. This is 1,000. So I have to carry at least 5 significant digits in the intermediate calculations, or I won't get this accurate enough for the final result that needs 5 significant digits. That's the difference between decimal places or significant figures and significant digits. Significant figures tells you where you stop the rounding, but significant digits tells you count over how many digits they have from the left one to the last one on the right that's valid. All right, so there's the height of the tower. That's what we want. Now I want to make sure I cover some of these new problems. The ones we did last time were kind of difficult. So this first problem here, it's over a bit. Here's 26. This isn't actually trigonometry, but arithmetic with these complex numbers is pretty easy. If you add them, you just add their real parts and you add their imaginary parts times I, and it's straightforward. Subtraction too. Multiplication, you just spoil. But division is the hard one. What if I ask you to divide 5 plus 2i? Good chance I'll do something like this. Divided by 3 minus 4i. I'd like to change the numbers. Remember, I'm going to give you similar problems to these and the ones out of chapter 8. And just change the numbers around, change the functions, maybe do cotangent instead of tangent, or maybe I'll change the sides of the triangle I give you something. What if I have a complex division? Remember how to do these? To do the division, you multiply the top and bottom by the conjugate of the bottom, right? So the conjugate of 3 minus 4i is 3 plus 4i. And that will make all the i's go away in the bottom and allow us to compute this quotient. Right? I can write down the bottom immediately. I know it's just 3 squared plus 4 squared. How do I know that? Memorization. Any number, a plus ib times a minus ib, we multiply this out. This is like the factor theorem in algebra with real numbers, is a squared plus b squared. Just like in algebra, a plus b times a minus b is a squared minus b squared. This is fundamental in complex numbers. A number times its conjugate is a squared plus b squared. So I know that, but if I don't, I'll just spoil it, right? This time it's 3 times 3 is 3 squared. 3 times 4i is 12i. Minus 4i times 3 is minus 12i. And sure enough, these cancel. And 4i times minus 4i is minus 4 squared I squared, which is minus 16 times minus 1. Which sure enough is 16, yeah. So you can do it the easy way, or you can just spoil it. Doesn't hurt anything. I'll give you full credit either way. So the bottom is going to be 25, right? 3 squared plus 4 squared. Top, not so lucky because they're not conjugates, right? I have to multiply out and see a FOIL. 3 times 5 is 15. See how I snuck in multiplication here too? Plus 5 times 4i is 20i. Plus 3 times 2i is 6i. Plus 2i times 4i is 8i squared. And then I squared is 1, so this is minus 8. So I have 15 minus 8 for the real part. And then I have 20i and 6i makes 26i. 26 for the real part. 20 plus 6 all times I. This whole thing, I'm sorry to go around again here. 15 minus 8 is 7. Plus 26i. All over 25. So there's the quotient of those two complex numbers. I will give you full credit for this. However, what I'd really like to see, the purpose of doing this is to put it in standard form, so it'd be better to put it as 7/25 plus 26/25 I. So here is a better answer, A plus IB, right, or A plus BI. Motion of these two complex numbers is this complex number with fractions in it. Be able to do that. And finally, I expect to ask you the following question, just with different numbers. This is the Malbridge theorem. Haven't written the test yet, but I plan to do this because this really tests everything. I love questions that test everything. I see if you learned everything. So 27 says, evaluate the expression using the Malbridge theorem. 2 plus 2 square root 3 I to the 6th power. Wonder what that could be. If I multiply 6 of those together, I'll probably make a mistake. And on the test, I might make it to the 20th power or something. Try doing that without a mistake. Huh? How can I do it accurately and without taking too long? I convert it to the polar form and use the Malbridge theorem. All right, well, I'm going to say, for that, I need the polar form of the complex. R is the square root of A squared plus B squared. No possibility of minus with complex numbers, right? Remember, polar numbers, you're going to let R be negative, but not polar form of a complex number. The positive, the non-negative square root. So it's square root of 2 squared plus 2 square root 3 squared. All right, whatever multiplies I is B. Be careful here, don't square 2 square root 3I with the imaginary part of the number is the number that multiplies I. It's a real number. All right, so it's 2 squared plus 2 squared 3 squared, no I in there. And square root of 4 plus 12 is square root of 16. R is just 4. That's a hint you got it right when you get a whole number. I don't guarantee whole numbers, but frequently I put them so you can kind of tell. Right? Tangent theta is B over A, an analogy to Y over X for polar coordinates, right? Is 2 square root 3 over 2. Oh, just square root 3. Now, what angle has tangent equal to square root 3? I want you to find it exactly. Decimal form, you might get something for it, but I'm going to take something off if you don't do this exactly. And it can be done exactly. What is the angle? Maybe it's the arc tangent, or maybe it's 180 plus the arc tangent, right? Remember, because there's two angles always. One's the arc tangent, one is the opposite, arc tangent plus pi, or 180. So theta might be the arc tangent of square root 3. I wonder what it is. Well, let's figure it out in the unit circle. What we want for these is R equals this non-negative square root, root some square, and then theta has to be the same quadrant and have this tangent. Well, A and B are both positive. You plot them in the complex plane, 2 and 2 square root 3. You plot the point right here, 2 plus 2 square root 3I is in the first quadrant. So you want this to be in the first quadrant, right? This is the angle theta, so it has to be in the first quadrant. What I do is I rewrite the square root 3 as here, as square root 3 over 2 over a half. Why do I do that? So this becomes a point on the unit circle, y over x or b over a, right? I just memorize that. Think of square root 3 as square root 3 over 1 is square root 3 over 2 over a half. You can also figure it out. You root some square these two. You take square root of square root 3 squared plus 1 squared is 2. And that tells you to divide the top and bottom by 2. But you don't need that. You memorize these, right? Now, if this is B and this is A or Y and X, is it in the right quadrant? It could also be minus this over minus this and have the same quotient. There's two cases, right? So there's this one, and there's minus root 3 over 2 minus a half. Well, this is in quadrant 4. We throw it out. We keep the one in quadrant 1. And now I look at it. Square root 3 over 2 for Y, 1/2 for X. Puts me up here, and I recognize that reference triangle, right? 1/2 square root 3 over 2, 1. That angle must be pi over 3. That's theta. Angle in the first quadrant with this quotient is pi over 3. Now I've got it because in polar form, this is also R times cosine plus I sine theta, right? So I'll write it in that form. R is 4, theta is pi over 3. And I'll take that to the 6th power. And in the polar form, it's easy to compute a power, right? Because if you take the nth power of this one, what does the Mulvey's theorem say? It's R to the n. You take the nth power of the radius. Cosine plus I sine of n times the angle. Remember, we did the 5th power. We took 5 times the angle. 1, 2, 3, 4, 5 last time. And we took the 5th power of the distance alpha. That's what this is. So we're going to get for this one, this time 6th power. So this one to the nth is R to the n cosine plus I sine n theta. We'll say 4 to the 6th times cosine plus I sine of 6 pi over 3. That's 6 times the angle. There is the polar form of the number that's the 6th. Now I want to convert it back to the standard form. How do I do that? I actually know what this is. If you're a computer scientist, you might find this interesting. Powers of 2 are really useful to them, right? Successive powers of 2. 2 to the first is 2, 2 to the second is 4, and then 8, 16, 32, 64. These come up all the time in computer science because you use bits and bytes and all that. 128, 256, 512, 1024. There's the first 10 powers of 2. 2048, 4096 is the 12th power of 2. If I think of this as 2 squared to the 6, this is actually 2 to the 12th power using algebra, right? 2 to the 2 to the 6 is 2 to the 12th. Do this on your calculator, it's just as good. I'm just saying for your education. That I memorized 2 to the 12th is 4096. So I could call this 4096 just out of memory. What's cosine plus I sine of 2 pi? We write it out. Cosine 2 pi, 6 pi over 3 is 2 pi. Cosine 2 pi plus I sine 2 pi. I know that. Cosine of 2 pi is the same as cosine of 0. It's 1, right? Cosine of 2 pi is the same as cosine of 2 pi is the same as sine of 0 is 0. And so this is just 4096 times 1 plus 0i. What number is that? 4096 times 1 is just 4096. This has nothing. It's the real number, 4096. Isn't that fascinating? You take this complex number, 6 power, and it's actually a real number because this angle right here is actually 1/6 of 2 pi, right? We went 1, 2, 3, 4, 5, 6, and it got you back in this direction. It gave you a real number, 4096 units out that way. So this answer here is just 4096. How about that? Able to do that for the final, good chance I'll ask you one like that because it's kind of pull all the complex numbers together. Makes you multiplying, all that kind of stuff. Use the polar form of complex numbers. Any questions on all that one? Well, I want you to be able to solve trigonometric equations. For instance, suppose I said secant of 2 theta is minus square root 2. Can you solve that? That's 25b. This is the last problem, I think. Solve secant 2 theta equals minus square root 2. On the interval, 0 to 2 pi. About that. What do you do when you see secant 2 theta equals minus square root 2 to solve? Immediately write it in terms of sine, cosine, or tangent. Take the reciprocal, and this means equivalently that cosine of 2 theta is minus 1 over square root 2 within the same range of angles. There we go. That one I can solve, right? I call this one, whatever my favorite letter is, phi equals 2 theta. And I say, I want to solve cosine phi equals -1 over square root of 2. This can also be written as by multiplying compound line by square root of 2 is minus square root of 2 over 2. Boy, that looks familiar, doesn't it? So I go to the unit circle to solve for phi. What angle has cosine, the x coordinate on the unit circle, equal to minus square root of 2 over 2? It's right here, right? You draw the vertical line and say, oh, there's exactly 2 points on the unit circle that have that cosine. Wonder which one it is. Well, it could be either one. There's 2 solutions between 0 and 2 pi at least. So I find these 2 angles, and what are they? Well, since this is square root of 2 over 2 on this to here, this is a square root of 2 over 2, square root of 2 over 2, 1 triangle. This angle is pi over 4, and so is this one by symmetry. Right? So we can say there's 2 angles between 0 and 2 pi that satisfy there, right? B can be pi back up pi over 4 is 3 pi over 4, or it can be pi plus pi over 4 is 5 pi over 4. But wait, that's not all the angles. I can add any whole rotation. 2k pi where k is any integer. That's all angles phi. I want theta. 2 theta is equal to phi. So I take these things and I say, well, this is, I'm dividing the first one. Theta is half this, 3 pi over 8 plus 2k pi, plus k pi, because I divide this by 2. Or theta equals 5 pi over 8 plus k pi. Then you have to figure which of those are between 0 and 2 pi for I'm out of time, so I better just write this down real quick. The theta between 0 and 2 pi. It turns out that k equals 0 and 1 and k equals 0 and 1, and these give you the angle pi. So you get 3 pi over 8. 3 pi over 8 plus pi is 11 pi over 8. That's k equals 0 and k equals 1 in the first equation. Then the second one, same thing. K equals 0 and 1 gives you 5 pi over 8 and 13 pi over 8. That's the answer for that one. 4 angles. How about that? Hope you had a great semester. Maybe some of you going and seeing calculus or something. Next semester, it'll be nice to see your faces. Come by and say hi if you get a chance. Otherwise, I'll see you at the final.